penetration testing and offensive-oriented stuff. Similar to that, I do a lot of physical security stuff. So many of you know me because I taught you how to pick a lock at some point in life. So I do a lot of work with non-destructive entry, specifically lockpicking, safe cracking, as well as tamper seals and tamper technologies. So these are like drug packaging, food packaging, electronics packaging, like warranty, avoidance type things. And some of you might know me because I run the Layer 1 conference that's coming up in May over in Pasadena. You should all go. If you've never heard of it, ask me after. But it's LA's biggest hacker conference, and it's awesome. Slightly biased, but you should go. I also run Null Space Labs, or one of the people who run Null Space Labs up in Burbank. So this is LA's hackerspace. I would argue LA's only official hackerspace. The others are not hacker focused, but I digress. So if you want to know more about me, talk to me afterwards. What we're here today to understand is what is reverse engineering. So for many of you, you are students starting in the field and you don't know what you want to do, right? Some of you know you want to do red team stuff or offensive stuff, but you don't know what. Some of you know you want to do blue team stuff, but you don't know what. Some of you want to do DevOps, administration, yada, 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 right? So reverse engineering is kind of a nebulous field in that you don't just Google jobs for reverse engineering, right? It's very difficult to figure out how to get a job in this field, and frankly, that's hard because what it is hard, and it means a lot of different things to a lot of different people. The basic kind of thing you need to understand is that reverse engineering fundamentally means that we are trying to figure out how something works by observing it or interacting with it. And it could be different to different people, right? So some people think of this as a hardware thing, so hardware as in electronics. Some people think of this as a machinery thing, so figure out how a machine functions. Today what we're going to talk about is software reverse engineering. And when you hear cyber people talk about reverse engineering, that's probably what they mean, but it depends a lot on context. I'm also a super laid-back presenter, so if you have a question, just shout it out. Don't worry about it. So what is software reverse engineering? So what we want to learn about software specifically is what it does, how it does it, and we want to learn about hidden features. And for most people, what they're trying to do is figure out vulnerabilities in software. So there's a couple camps that do reverse engineering, but I would say it's not a common thing. If you go to company XYZ, it's very unlikely that they're doing reverse engineering. This is limited to people doing security vulnerability research, bug bounties, military, government, and very high-level corporate espionage. And that's kind of it, other than hobbyists, of course. So many of you probably heard about bug bounties. If you want to do most bug bounties for not web, so anything other than web hacking, what we're going to talk about today will be very applicable. This is also for kind of generic security research. So when you see people find zero-day or new exploits in Windows or a browser or pretty much anything, typically it's based on reverse engineering and exploit development and that sort of thing. Obviously for malware research, malware is one of the only forms of software that really tries hard to prevent you from understanding how it works. Because if you understand how it works, then you can understand how to block it, you can understand how to filter it before it gets into your network. Obviously for government, military, and intelligence, this is a big thing for figuring out how another country's airplanes work or their weapon systems, right? These are all deeply rooted in electronics and technology now. It's very rare that there's a weapon system that has no onboard electronics, no navigation, no guidance that's controlled via electronics or software somewhere along the way. And then obviously for many of you, hobbyist hackers and CTFs. So the place you're going to get the most experience with this is doing CTFs and just hacking stuff, right, for fun. If you've never done a CTF stands for Capture the Flag, and it's a cyber wargaming competition where you take something apart, figure out how it works to figure out the answer, and the answer gives you points, and then you high-five your friends. And it's extremely boring, as all of you saw before the talk, right? So the first thing we need to understand about reverse engineering is how does software work, right? Like fundamentally, you can't just start by digging into these very low-level parts of software. You got to kind of know the flow of how it works, right? So first things first, you write software. What do you write your software in? Programming language. So you write source code, right? This is a human-readable version of what you want your program to do, right? And this takes a lot of forms. Obviously, there's lots of different languages and lots of different syntax and all that. But effectively, you write your source code. Sometimes, very often, you're using a library. So this is code somebody else has written that you use, so you don't have to do the hard work of writing it to reinvent the wheel, so to speak, over and over. All of that gets put into a compiler. The compiler produces assembly code. So assembly code is a different kind of source code that's tied to the architecture in which you're going to run it. So by architecture, people mean, is it an Intel chip? Is it an AMD chip? Is it PowerPC? Is it AVR, et cetera, right? All these different processors have their own type of assembly. So the assembly code gets put into the assembler, which makes an object file, which is just an assembled version of the code. And we'll talk about how this works in a second. After that, all of this gets passed to the linker. So what the linker's responsibility is that you ask for library resources. You say, I need the XML library, I need the HTTP library. And the linker's job is finding that on the current system and linking it together with your code so that when you ask for it, when you're running your software, it knows where to find it. Right? So far, so good? Comp Sci 101? Data, what am I doing here? So after all this, you get an executable. So technically, the object file as assembled is executable, so to speak, in that it's real code that could be executed. But the linker puts it all together in a way that packages it for your operating system. So you'll get an exe file, or in Linux and Mac, you'll get an ELF file. So far, so good? It's not like a normal class. You guys can ask questions and interrupt the teacher. If I could reach one person. So your question is, well, Data, I don't write compiled languages. Those are old and archaic and whatever else your professors taught you to say about what's good and what's bad in programming. So the real answer is that there's not a whole lot of difference between a compiled language and an interpreted language. It's just where that compilation to assembly happens, so to speak. So in an interpreted language, say Python, Java, etc., you're doing kind of the same thing. You're writing source code, which uses library code. That gets put into a bytecode compiler. So what bytecode is basically a middle ground between machine assembly and source code. It's kind of like a language-specific assembly, right? So when people say, is Python interpreted or compiled, what's the answer? Yes. Yes is the answer. Because technically, you're getting compiled to bytecode, and then you're getting interpreted by the bytecode interpreter, which is written in C or C++ or something not interpreted, right? So it's basically the same, other than your code is executed via a virtual machine. So in Java, this is called the JVM, the Java Virtual Machine. In Python, this is called the Python interpreter. And the same goes for Ruby, Perl, PHP, any other, quote, interpreted language. But the goal of this is that at the end of the day, no matter what language you're writing in, it is running in assembly on the chip you are running it on. It doesn't matter what the original language was. Okay, so now we know kind of how software works. Let's talk about how do processes work, right? When you click your exe in Windows or when you run a command in Linux, what happens, right? So there's a whole bunch we're not going to cover for time reasons, but basically it magically gets its own virtual memory space. So if you think of every process on a system as a house on the block, and it can do whatever it wants in its own house, and as long as it doesn't try and go outside of its house and smash its neighbor's window, it's okay, right? So if you're old like me, you'll remember old operating systems, so Windows ME and before, where stuff would just crash. You would just kernel panic or blue screen, still can happen, but it's much less common. This is because in the old days, any process could affect any other's memory. So if one process went bad, it typically had ramifications on the entire system, which caused a big system crash. Now you'll get an exception for the program, because the operating system knows, hey, you caused a problem in your house. Something's wrong with you, but everybody else is okay. So the basic breakdown of virtual memory, at least on Linux, and this is for 32-bit, it's more or less the same in 64-bit, just the numbers are bigger. But you have some segment of code set aside for the kernel. So you probably all know what a kernel is, but kernel is your operating system component, so more or less. You have a stack and a heap. So the stack is used for function variables and control flow effectively. So when you have a function, call a function, call a function, they use the stack to keep track of how to get back to the function that called the function that called the function, and so on. The heap is a little different. This is for dynamic memory. So think of like a web server. As it gets a request, it will allocate some memory to be used for the handling of that request. That would go in the heap. And then you have data and BSS. So these are data that you defined or set space aside for during the programming process that you don't know the values of or have static values. So these are like things like strings. You type in, the name of the string is ABC, right? That gets stored in data or BSS depending on the specifics. And then you have the text segment, which is all your program code. So all that assembly and all that linked assembly block, that all gets put in the text segment. Okay? So for the most part, when you're doing reverse engineering, you care about the top couple. You do not care about the kernel unless you're specifically going after kernel level vulnerabilities or kernel interaction, right? So typically, you don't want to touch that part of memory, because if you mess it up, you crash the process and bad stuff happens, right? Okay. So when people talk about reverse engineering, there's two kind of approaches. There's static and dynamic. So static refers to everything that doesn't execute the program, right? So when you're looking at a software statically, you can disassemble it and decompile it. And if you don't know what those words mean, we'll talk about them in a second. You can look at what libraries it requests. You can look at information provided in the executable or the metadata of the executable. And then you can also get string data. So this is data stored in printable text within your program. So the big difference, again, static, you do not execute the code. So why wouldn't you want to execute the code?
It could be malware.
It could be malware, right? You don't know. It's a hard problem to solve if a given arbitrary block of assembly is going to do good things or bad things, right?
Also, is there I'm pretty new to reverse engineering. Aren't debuggers also really loud in terms of they're really easy to detect? Like if you have a debugger in runtime.
The question is, are debuggers hard to detect? And or easy to detect? I'm going to go back to that when we explain to everybody else what a debugger is, if that works. But the answer is yes and no. It's another hard problem for both sides. But we'll talk about it more in a bit. So static, do not execute the code. Like dynamic, execute the code. So the difference here is that you, as the reverse engineer, may not see all the things that the software does just by looking at it statically. So imagine if the software just accepts an input and then does whatever the input says. You don't know what the input might be from a third party, right? You can't test every possible input and know every possible consequence of that. So there is dynamic reverse engineering. So typically this is done with the aid of a debugger, which we'll talk about in a bit. You could do runtime disassembly. So this is different than static disassembly. Disassembly, again, we'll talk about, is taking the program apart to see what the assembly code is. And it can be different when it runs versus when it's sitting on the hard disk. Other things you could do is that you can monitor access to system resources, so specifically files, network sockets, library calls. These are things that aren't easy to do statically for the same reason that you can't know everything it does statically, right? And most reverse engineering is a blend of both. If you're doing malware research, they have what's called detonation sites. So you can submit your executable and they will run it in their fortified thing, and they basically, it's like a bomb squad, right? They just push go, and whatever happens to that VM happens to that VM. And I don't frankly understand how it works on their end, but I guess they just hope that there's no VM breakout or container breakout that compromises them.
It's not like there's documented vulnerabilities on them.
Yeah, so like a week ago, there was a Docker container breakout. So don't think of virtualization as like it's actually isolated, because what did we learn? At the end of the day, you are running code on that processor. And if that processor is shared with the host OS, then by definition, if you get the right vulnerability, you can affect the host OS or the hypervisor or whatever it is, right? So we're going to talk about a couple kind of key things. We're going to talk about disassembly, decompilation, and debugging. And these are kind of the fundamental building blocks you need to reverse engineer. So make no mistake, you will not leave here ready to test malware and take apart the next Stuxnet, because frankly, we have 45 minutes, and what can I do, right? So we're going to talk about what these things are, just so that you understand what they are. And then for the 0.1% of you who are actually masochistic enough to continue on this path, you will have a good starting point for what to learn next. So let's talk about disassembly. So we learned that when you get your source code gets turned into assembly code, right? And then your assembly code gets turned into object code or an object file, which is binary or the compiled final version of your code, right? So disassembly is the process of going from your binary code back to assembly language. Now this sounds hard, but assembly is actually a mnemonic language. And what this means is that there is a direct translation for every possible instruction back to the assembly based on looking at the binary bits. And this is what your processor does to figure out what the thing you're trying to execute is, right? So for example, this instruction, doesn't matter what it does, don't worry about it, don't get scared. So Zor rax has this direct translation in 64-bit Intel assembly. So when you look at your executable, if it has this instruction, it will have these 3 bytes sequentially, right? And this can be different based on if it's a 64-bit binary, if it's a 32-bit binary, if it's for Intel chips, it's for PowerPC chips. They all have their own magical assembly language, right? So far, so good? I know, it's scary, right? There's hex on the screen. So how does this work? So again, effectively every single possible instruction has a direct mapping from the binary bits back to what the instruction text should be. Again, it's a mnemonic language, which means you can translate back and forth easily. So what your CPU does is it says, hey, I am pointing to this instruction. What does that instruction do? And how do I do it? So it starts reading the bits. It figures out, oh, okay, if the first however many bits are zeros, I'm supposed to do an add instruction, add 2 things together. And then based on all the other bits, it determines if you're trying to add a fixed value to memory, a fixed value to a register. A register is like a variable in your processor. It tries to figure out if you're doing register to register, memory to memory, and all the different variations of how you can add 2 things together on the given chip, right? And then at the end of the day, it figures out, all right, you're trying to do this, and that means this. Right? And that all gets translated to binary. So fundamentally, disassembly is very simple, right? A single instruction, given its bytes, is very easy to disassemble. Everybody agrees so far? Now I know you'd have to look it up, but don't worry, there's a library that does this for you. But there's a fundamental problem in computer science and processing and the way we do this that makes disassembly hard, especially if you are manipulating the outputted assembly or the output binary, right? So the first consideration, really the biggest one, is that disassembly requires a valid starting point. So what this means is that when you just look at the middle line here in black, right? This is just a bunch of jumbled up bytes, right? I realize they're not hex, go with me. Right? So this, you don't know what this is. It just looks like gibberish, right? So if you start at the first letter, in this case A, you get the following blocks of different instructions. Now, this can be addressed in certain other assembly languages. In Intel, you have variable width instructions. So some instructions are 1 byte, some are 2 bytes, all the way up to 15, 16, 17 ridiculous byte instructions, right? In other architectures, you may have a fixed length. So you may have every instruction, no matter what, is always 3 bytes or 4 bytes, making it a little bit easier to disassemble. But let's get real. Nobody else uses anything but Intel, so it's fine, right?
Yeah, ARM just totally doesn't exist.
They exist, but let's be real. Like, the reason you learned pin-tumbler lockpicking at the lockpicking class is because 90+% of the world uses the pin-tumbler lock, not because we thought it was fun, right?
A lot of people have these little supercomputers in their pockets.
Right? All running Intel. In any event, so if you start at the wrong spot, you get different outcomes, right? Because it's reading the bytes differently, therefore interpreting what the instructions are differently, right? So it'd be very challenging if you start at the wrong spot. Now you're saying, well, how does the processor know? Well, your binary, your executable that you make, has a starting point. It says start here. And when it's run, it knows, all right, I start here, and then processes sequentially until it crashes or finishes. Okay? Does this make sense, this fundamental idea?
So, because everything's in numbers, and if you start at the wrong number, it just mixes up the entire thing.
Yes. If you start at the wrong number, it will interpret it differently. Because you're saying, instead of the instruction AB, you're saying BC, for example. And that is fundamentally a different instruction as interpreted by the processor. Okay?
Wait, you mean starting point? You mean like the EIP or just?
Yes. So when your process starts, again, it has an entry point, and once all the process setup is done by the OS, it says start here. And it starts literally reading in the bytes and figuring out what the instructions are and executing from there. And it has no knowledge of where it's been or where it's going to go for the most part. Okay? So there's this concept of different forms of disassembly. So there is linear. This is where we're going to read each set of bytes, and we're going to interpret what they are, and then we're going to read the next set of bytes and interpret what they are, and so on and so on. This is linear disassembly. We read it like microwave instructions, right? Number 1, do this. Number 2, do this. Number 3, do this. So if there's a problem anywhere in the middle, it breaks, just like in our example. There's also what's called recursive disassembly. So this is like the same concept, but a little bit smarter in that they use contextual clues to figure out what's valid code and what's not. So for example, all the variables you define in your program are assigned an address. It's assumed that anything the programmer variabilized is a legitimate address, right? If you branch, so this is when you call a function or go to another part of code, when you branch, it's assumed that the target after the branch and the target at the branch, the location, is valid code. Because otherwise, why would you ever do this? There's also a little more fancy stuff, so they figure out there's like a signature for when a function starts and stops related to cleaning up of the environment. Some disassemblers will look for this to try and identify functions. Okay? So recursive, more fancy, linear, dumb. If there's a problem, linear will break. So this is an example. Again, I know you don't know assembly. It's cool. But let's imagine we have a bunch of instructions. Instructions are typically called opcodes. So you got instruction 1, instruction 2, and then we're going to say jump down here. Jump to start 2. So we're skipping whatever is in the middle. Now, a linear disassembler will correctly disassemble opcode 1. It'll correctly disassemble opcode 2. It'll correctly disassemble the jump. But if we put junk after the jump, then it's going to assume it's valid assembly and try and parse it, again, like microwave instructions. It's going to go, hey, whatever that is, cool, that's an opcode, let's interpret it, right? That'll lead to bad assembly. Okay? Recursive disassemblers are a little bit smarter in that they can use some contextual clues to mark what is valid and what's not. So in this case, the recursive disassembler is going to look where the jump goes and say, hey, wherever that jump goes, that is probably valid code, right? Does this make sense? And in doing so, it's going to figure out, hey, whatever's in between, probably not good, either by determining it's a bad instruction or determining that there's a conflict between where the jump goes and what the next instructions are. I know, this is hard. Your brain's hurt. It's okay. It'll be over soon. Okay? So let's get, I dare to say this, but let's get a little more advanced, right? So these are easy problems for us to figure out, fundamentally. 1 equals 1, is this true or false?
True.
1 equals 0, is this true or false? These are not trick questions, right? These are easy for us to figure out, right? What about the third one? Is the third one true or false?
True.
Sure? No, I'm just messing. It's true. I'm just messing. Okay? Right? But a little bit harder, right? So assume that any evaluation is infinitely complex within the bounds of processing time. What this means is that the first two examples are very simple for us to figure out, but maybe very complex and time intensive for a processor to figure out, right? What about input 1 equals input 2?
It would depend.
You don't know.
If
You don't know, right? So how's the disassembler going to know? Right? It's hard. It's a hard problem. It's fundamentally, I wouldn't say not solvable, but fundamentally very hard. So what if these decisions are used to control where code goes? Right? So far? Okay, so this brings us to this concept of OPOC predicates. So these are evaluations which depend on runtime data. So via static disassembly may be very hard or impossible to figure out how the code's going to work because of this, right? And just like it's hard for us to predict, it's also hard for the disassembler to predict. And there's a time limitation. Like the disassembler is not going to brute force all the possibilities and figure out where they're all going to go, right? It's going to go, I don't know what to do, help me, right? Or give up, right? So some examples in assembly are if you're jumping to a fixed address, the name of a function or the address of a function, this is an easy thing for the disassembler to figure out. If you jump to the value in a register, the disassembler doesn't know where that goes until it's time to do it, until it's actually executing, and it can make a decision about where it's going to go, right? So you're like, fine, no big deal. We'll look at runtime, right? No big deal. Well, okay, so this gets even harder, right? So recursive disassemblers make assumptions, and assumptions are awesome for people writing malware because they lead to problems, right? So recursive disassemblers, we talked about this a little bit before, they make certain assumptions. So any code that points, that a jump or call instruction points to is considered valid, right? Because if you jump to address X, you must assume address X is valid, right? If you call, there's a function call address X, you assume it's valid. They also make the assumption that any code after a non-conditional jump or call is valid, because the assumption is you will come back to this at some point, typically. So, and anything at a symbol address, so this is if you name a variable something, anything at that address is valid, right? There's a couple other ones, but these are kind of the big ones, right? So what you could do is you combine this concept of OPOC predicates, where you don't know the truth or falseness of an evaluation, with where your code goes. In doing this, you can cause the disassembler to think there's code where there should not be code, or think there isn't code where there should be code, and et cetera, right? It gets, frankly, super complicated, and I tried to put it on one slide, but I couldn't fit it in a way that was like meaningful and legible to you guys. But trust me that this works, and it's very complex, and shenanigans, right? So the end result of this is shenanigans. Disassembly is very, very hard. So what else can we do? Well, we can debug it, because with a debugger, which we'll talk about in a second, can look at every single instruction as you're running it, but there's also shenanigans there, right? But just remember, disassembly hard problem. I know you all have taken like one semester of comp sci and you're ready to tackle this, get after it, but it's actually quite hard. So for those of you looking to learn more about disassemblers, the kind of gold standard for disassembly is IDA Pro. IDA Pro has a free version, but it is nowhere near as good as the paid version, and the paid version is moderately expensive, in the thousands of dollars range. However, it is awesome. It's really good. If you're looking for some free alternatives, I should also mention IDA Pro is recursive. There's free versions are Object Dump, NASMs, NDisasm. These are both linear disassemblers. There's Hopper, which is not free, but it's like a $50 debugging and disassembly software that is very popular. Hopper is also recursive, but any recursive disassembler still has problems if the binary is written a certain way. So also Binary Ninja. Not sure if this is recursive, but this is another very popular one. You might see Capstone if you're looking at disassembly projects. Capstone. Capstone is a disassembly framework, so effectively they provide a platform agnostic API, so to speak, to say here's binary, tell me what the assembly is for a given architecture, and they figure out, oh, this is Intel x86, here's your assembly, and so on, right? Another note is that all debuggers come with disassemblers. So not listed here are things like GDB and IDA Pro and others. All debuggers have disassemblers. Question?
Have you tried Ghidra?
Question is, have I tried Ghidra? Yeah, but that's funny that I forgot to put it on here. Ghidra is the NSA's open source disassembler. A key point is that Ghidra is not a debugger. It is only a disassembler, but that's a good call. I forgot that. My bad. Okay. So far, so good? This is kind of like a scared straight program to figure out if you really, really want to do this. So next thing we're going to talk about is decompilation. So decompilation is the process of going from your executable/assembly back to source code. So going from executable to assembly is kind of easy in the sense that the translation process is easy on a per instruction basis. But going from assembly to source code is very difficult. And the reason for this is that you lose a lot of data necessary to figure out what the original source code line was. Another thing here is that valid disassembly is required for decompilation. So you can't wing it, right? If you want to know what the source code is, you need to give it as much information as possible. And with invalid disassembly, you're going to get invalid source code. It's not going to make sense or not be possible, right? Most decompilers will decompile to C or C++. So the key note here is that that may not be what the program was written in, right? So maybe it was written in Rust or Go or something else, but decompilers don't decompile to Go or Rust or whatever, right? They typically decompile to C, and a couple of them support C++. The things that make this hard is that there's a lot of data lost in the compilation and decompilation process. So when you compile something, typically you're going to lose function names and variable names. This varies, right, based on your compiler settings and the language and blah, blah, blah. But you are going to lose these. So instead of your fancy variable names and function names, you'll have memory address locations, which is not the easiest to understand and figure out what goes to what. Because when we have, function print and function read and function write, these make sense to us. But when it's function 1, function 2, function 3, it gets more complicated, right? Things you're also going to lose are source code comments. So very common that you're not going to have the benefit of seeing all their comments. This is people are very surprised by this, but it's funny to me. Another big thing is that code can be optimized or changed by the compiler from what the original code was. So if you do like something stupid like this third line, the compiler is going to be like, dude, I already know what that is. I got you 7, right? Like it's not going to worry about doing all these calculations at runtime because you're providing a fixed literal value, right? So the compiler can and will change code.
Compilers are nuts.
Yeah, and they do crazy stuff, right? So, right? Does this make sense? You lose information, makes it hard.
It's fun. It's just extra fun.
Oh, okay. So some common decompilers are hex arrays for IDA-Pro, and man, if you thought IDA-Pro on its own was expensive, wait until you see the price for the decompilers. They are insane expensive, and they are on a per architecture basis. So there's an Intel decompiler, AVR decompiler, and so on and so on, right? This is into like the $20,000, $25,000 range to get just a couple of them. They are very expensive. Ghidra has a built-in decompiler, which is pretty good, at least for Intel architecture stuff. And as I mentioned before, Hopper has a decompiler. There's also Snowman, which is built into x64 debug, which is a Windows debugger, 64-bit Windows debugger. And then there is RetDeck, which is kind of like Capstone is the API for disassembly. RetDeck is the API for decompilation, right? And not a lot of projects use this, but it is available, right? So again, gold standard IDA-Pro all day long. Ghidra, pretty good for free. The question is, where is DNSpy fit in? So DNSpy, if I'm not mistaken, is a .NET. It doesn't. I don't know that it fits into a single category, but the .NET is its own weird thing, which we'll talk about in a second. But effectively, .NET, for all intents and purposes, counts as an interpreted language. So .NET builds in a lot of stuff like Python and Perl and Ruby and so on, that kind of fits it into this other category. Like technically it's assembly, but technically it's interpreted. So it would be kind of on this list, but not specifically for these. These are kind of the normal ones. Okay, so on this point, let's talk about decompilation of interpreted languages, right? So we have a bytecode object, right? How do we go from bytecode back to source code, right? So remember, difference between compiled and interpreted languages like Python. In Python, you're going from Python source to a PyC file, which is compiled Python, which is Python bytecode. Same goes for Java, Perl, Python, .NET. All of these are effectively interpreted languages. So these are different. These are very different because by default, almost all of these languages provide a huge amount of debugging information in the the output object, right? So in an executable, you lose a lot of data, but in these languages, they leave it all for you, for the most part. And again, another big difference is that these decompile back to their original language. So the Python decompiler goes from Python bytecode back to Python, not to C or C++, right? So these are very interesting because they include debugging data, so specifically variable names, line numbers, sometimes entire source is included in these depending on the language and the settings, the default settings for the interpreter or compiler. These also have very minimal instruction sets. So Intel, as an assembly language, has hundreds of possible instructions. The Python one has something like 40, right? And that's being pretty generous. Like most programs do not use all 40. However, these decompilers are very easy to break. So because nobody's doing this in the sense that nobody's making obfuscated Python bytecode malware, there's no need for a recursive disassembler or a recursive decompiler or any other fancy stuff. Again, remember, disassembly is a requirement for decompilation. So whether you're in Python or in C, you still need valid disassembly. So if the Python disassembler breaks, you can't decompile it and can't get back, right? So again, just to reiterate, there's almost no recursive disassemblers for interpreted languages. Yep.
So for .NET, you said .NET was an interpreted language. So would it also fall into this category?
Yeah, the question is .NET fall into this category? So I wouldn't say it's interpreted, but it definitely falls into this slide more so than the other slide in that you can go almost back to direct source for a .NET binary as compared to a C binary, a C++ binary. And it's because of, it's very similar in this regard to Python, Perl, et cetera. Right? So I didn't put it here, probably should have. But the program they're talking about is DNSpy, so .NET Spy. There's also ILSpy and .NET Decompiler and so on, right? These are very popular for .NET specifically. For kind of the big four interpreted languages, you have Python's uncompile, Java is JAD or JADX, PHP is unPHP, and Ruby is very, very creatively named Ruby Decompiler. Okay. There's also a Python decompiler, but you know, can't make fun of your boys, right? Everybody gets decompilation? Sort of? Kind of, sort of? Yes, no?
So
Everybody asleep?
you're using binary, you're converting that into assembly, and then you convert that into your language, and then
Yes.
you implement that.
Yes. Okay. Okay, so let's talk about debuggers. I'm going to have to go a little bit fast because we're behind schedule, but that's okay. So debugging, shocking, is to debug a program. This is why these exist, right? So the basic explanation of this is that you're going to watch and or manipulate a program while it's running, right? And I don't mean clicking the GUI buttons. I mean you are looking at it from an assembly or very low-level point of view while it's running. So the basic features of all debuggers are runtime disassembly, right? Because you have to be able to disassemble it to see what it's doing, to interact with it. You can start, stop, and quote, step execution. So what this means is that you can specify where to pause. Step is to execute a single instruction at a time. Very common things are you can view, dump, or modify process memory, right? So imagine something that is asking for a password. You can see if that password it's asking for is stored in memory, because at some point it has to do a comparison of your input versus what it wants to check for, right? Other very common things are see what open files it has, network sockets, right? We talked about this a little bit earlier, right? All the things it's doing at runtime that you can't see statically. Okay. So the way, again, to think of a program is a long list of instructions. And at any given point, the processor is executing one instruction. This gets a little funky with multi-threading and all that, but just bear with me, right? So in our example, we are at opcode 2. This is where we are. There's a literal pointer on the processor that says this is where I am and this is what I'm doing, right? And at any point in execution, we can pause the program to look at CPU registers. Again, this is internal state of the CPU. We can look at memory, network, files, etc., right? So first thing you're going to learn when you start working with debuggers is breakpoints. So you specify an address to break at. So this is where you tell it, when I get to here, I want you to stop, right? You can stop as soon as you start the program. You can stop when you get to a given function, right? Like the check password function, for example. And once you're there, you can continue, which resumes execution. You can step through execution one by one, execution of instructions. You can also, again, read, modify CPU registers, memory, et cetera, right? There are both software and hardware breakpoints. So hardware is a literal hardware-assisted breakpoint, like the CPU provides a functionality for this in hardware. But for the most part, what you're doing is software breakpoints. So when you go into a debugger and you say break on this instruction or break on this address, what it's doing is that it's literally overriding the code at that address with an interrupt, typically this int3 instruction. And when execution reaches that address, it causes an interrupt, which causes the operating system to go, oh, what do you want to do? And when it does that, it hands off control of the process to the debugger, right? So you can have multiple breakpoints. You can have conditional breakpoints, like I want to break at this function, but only when such and such arguments and blah, 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 right? As extensible as you want it to be. But this is the basic idea, right? So if you want to get started with debugging, some common debuggers for Windows, WinDebug is quote unquote the best, but it's also one of the hardest to learn. x64 debug and Ollie debug are very common Windows debuggers that are a little bit easier to use. The reason WinDebug is, in quotes, better is that Microsoft makes it, which means that by itself it understands kernel internals. So it understands more things that are effectively proprietary than the open source, kind of homemade debuggers do. So if you want to do any kernel exploitation or driver exploitation in the kernel, you probably want to use WinDebug so that it automatically understands all the file structures and whatnot. Okay. If you're using Linux or Macs, typically what you're going to be using is GDB or R2, radar, not sure how we say it. I also put a note here in that GDB and R2 are all platforms, so you can use this on Mac, you can use this on Windows as well. I think it's pretty uncommon to see people using GDB in Windows, just like philosophically, I guess, people don't want to do this. But they do have a Windows version that you could use. And then for things that kind of apply to everything, you have IDA Pro, again, good tool. I think people use it more for the disassembly and decompilation features, but it does have debugging capability. There's also Immunity Debugger is very popular, especially if you've done any kind of open source training stuff.
What's your opinion on remote debugging?
We'll talk about it in a second. There's also Hopper and Binary Ninja, right? So one of these you will like for the given OS you're targeting. I personally am super old, so I love GDB. I've learned to love it. But find what you like and do it. It doesn't really matter as long as you get what you want to get done, right? The question was, how do you feel about remote debugging? So remote debugging is something we have not really talked about in this, but effectively what you're doing is you have your testing PC, and then you have a target PC, and you run the software on the target, but debug it from your side. And effectively the way this works is that it just establishes a network communication back so that you're effectively debugging on the target, you're just doing it on your end.
And all the execution, the runtime, that's on the victim,
right.
Nothing's touching
Right.
the host.
Right, so this all executes on the victim or target machine, not your testing machine. It's fine. It's the same as making an SSH session into the target and running GDB or whatever manually. Just a little more convenient to have it automatically connect back in.
That's weird.
I don't think it's good or bad, it's just different. Okay. All right, so you're here and you're like, dude, can I go yet? Some of you are just waking up. It's a really exciting moment for me. I know, this is hard, right? There's a lot to learn. But don't worry. Don't worry. It's not that bad. None of you are going to do this anyway. It's not that bad. What? These are facts. All right, so if you want to get started with RE, the things I would recommend as far as like the easiest to use, I would say do Linux. Windows is different in a way that makes it harder to immediately learn. Combine this with the fact that there's many more resources to learn about Linux, whether it's the file formats or the debuggers or the tools or whatever, right? Linux is easier to learn and easier to work with, and easier to find resources for. So if you're doing disassembly, as far as if you want to stay 100% free, get Ghidra, get GDB. debug with Ghidra, or sorry, disassemble with Ghidra, debug with GDB. You can also use R2. R2 is excellent. I personally don't use a lot of debugging with it, but it's very good for disassembly and analysis on the static side. And then if you want to get into decompilation, try out Ghidra. Ghidra, it's literally just a button. Like, it's not like you're manually filtering all the assembly and coming up with source code. You push the button and up pops code. And it might be shitty hard to read code, but it's code, right? If you want to get fancy, get IDAPRO Hexrays. After you get this, you will be spoiled for life and never want to use anything else because it's so damn good. But it is, if somebody else buys it for you, it's well worth trying out, right? So those are tools. Some of you like books. I myself like books quite a lot. If you want some books, these are some good books. Pretty much all reversing or binary analysis focused. If you want to learn IDA, there's the IDA Pro book. They all cover basically the same things, like how to use a disassembler, how to use a debugger, how to look at assembly and figure out what the source code would be, effectively how to manually do decompilation for complex cases. And lots of other stuff, more practical examples. Question?
Yeah, so like you said, it's really, really difficult to do.
Yep.
But like, what would be a good program to start trying to dissect or something? Like, what's a good starting point?
Thank you, audience plant. So the question is, where do you start, right? This is a hard question for everybody. Luckily for you guys, it is 2020 and there's actual stuff to learn on. Myself, as a youth, I would like type in stupid C code and then compile it and then take it apart and be like, I figured out my own code, right? You don't have to go through that. You should for fun, but you don't have to, right? So I think the single easiest way to do this is either CTFs, right? Specifically CTFs that have reverse engineering problems, or crackmes. So crackmes are effectively only reverse engineering. It's like, give me the password, give me a valid serial number, which is not a fixed singular value, right? Or figure out how something works, figure out how to do this. There's a hidden function in this software, figure out how to do it, right? These are by far the best things you can do. Just, it doesn't matter if they're hard, right? It's supposed to be hard, right? Not everything is going to be like push F5 for decompilation, right? So do these. Find CTFs that you like. So I would recommend Pico CTF is really good. Pico CTF is a permanently online capture the flag that is very beginner focused. So it says it's marketed at high school students. Don't be offended. It's okay. It's marketed to high school students every year, but they start very basic, but they get very hard to the point where they're legitimate, challenging problems, even for professional CTF teams, right? If you're looking just for CTFs in general, you can go to CTF Time. Over the Wire has some CTF-like stuff, but it kind of blurs the line between CTF and penetration testing. It's more be on a system type CTF, right? Like privilege escalation type stuff rather than exploitation or reversing. And then crackmes, again. Crackmes are excellent. I would strongly recommend you look up how to set up a secure VM or something and not just run code from the internet, because that's how people get hacked. Right? All those people you make fun of with like their browser covered in shit, could be you. You know what I'm saying?
Yeah, I hear you.
Okay. So I strongly recommend these. Just start small. Eventually, you're going to fail nonstop for hours and hours and days and months and maybe even years. But eventually, you're going to solve one, and you're going to be like, ugh! You're going to be like in that Breaking Bad scene where he finally gets the cash and he's like, ugh! And then you'll never be able to stop. Question.
What are your thoughts on using Pwn tools?
Question is, what do I think about Pwn tools? So Pwn tools is a Python-only library. I use it in Python. It's a library used for assisting you with like the drudgery of exploitation. So like sending bytes over a UDP socket multicast to an address. Pwn tools just does that for you. Or packing data in a certain way, Pwn tools does that for you. Or you have a site and you want to keep running this command over and over until you get a specific result. Pwn tools does it for you. Pwn tools is excellent, and you should learn how to use it. I wish I knew more about it, but again, I'm old and set in my ways and stupid. So yeah, it's a PWN tools, if you want to look it up. And I believe it's definitely Python, but they might have other language bindings.
Ever heard of Pony Island?
Have I ever heard of Pony Island?
It's a
No, I have not.
It's another CTF. Basically, it's
Okay.
it's a MMO video game, but it's full of exploits. It's basically it's just a really complicated crackling
Okay.
that
Yeah.
teach developers not to do particular.
So the
things.
hint is, not the hint, but the discussion, if you didn't hear it, is Pony Island is a game-based CTF.
Yes.
Is it always online, I assume?
Well, it's
You download it.
Yeah, you download it. It's offline, but it's full of exploits on purpose, and it's just teaching
Yeah.
developers not to do.
Yeah, there's lots of stuff. There's like, damn vulnerable Linux and damn vulnerable web app and whatever. For whatever you're interested, there is a thing for it that you can download.
This one's like specifically for reverse engineering.
Okay, cool. Okay. So I'm not here just out of the goodness of my heart, obviously, right? Come on, you guys are no fun. I'm trying to have fun here. No, but like I said at the beginning, I run Layer 1. You should come to it. If you haven't talked to me at the table, it's a hacking and technology conference, an InfoSec conference in May up in Pasadena. I know what you're saying. Oh my God, Pasadena. It's like 20 minutes away. Oh my God. You'll live. Drive. You'll thank me. Oh, it's so far. It's like another state. I know. You'll live. Drive. You'll thank me.
Free parking?
It's Los Angeles, man. Is there free parking?
Nobody can free parking.
There's no free parking, not even in Monopoly. Take the train, fly, whatever, right? Anyways, if you are interested in anything, hacking, electronics, programming, lockpicking, gaming, having fun, parties, whatever, drinking, whatever, we have all of these things. We are known for being the most hands-on conference, so everybody is doing stuff, whether it's a CTF or an event or just having fun. So I hope to see you there. Right now, tickets are discounted. It's $120 for both days. Oh, come on, student. It's fine. You get breakfast both days, a banquet dinner, all you can eat on Saturday night, as well as an electronic badge. Yeah, that got you excited, huh? Right? So I hope to see you all there. If you have questions, hit me up at the booth outside afterwards. And thank you for coming.